Okay, great. We're gonna get started. Um, First of all, thank you for joining our webinar today. Before we begin, let me give you a brief introduction. My name is Ming Zhou, and my background is in chemistry. I've been with MVA Scientific Consultants for 6 years now. MVA Scientific Consultants is an analytical microscopy lab. We offer customized electron microscopy imaging, analytical testing, investigative analysis, and ongoing R&D supports for a variety of industries. Our speaker for today is Jake Spry. I'm going to give you a brief introduction on Jake. Jake graduated with a Bachelor of Geology from the University of Alabama in 2011, and then he obtained a master's degree also in geology from the University of Alabama in 2013. Jake's master's thesis project involved HRTEM and also STEM imaging and analysis of magnetite nanoparticles. Jake's TEM experience involves working with asbestos nanoparticles, soot, and carbon nanotubes. Today our topic is on high-resolution TEM imaging of nanomaterials. So without further ado, I'm going to let Jake take over.
All right, thank you, Ming. I also would like to thank you and welcome you to this webinar. I'm excited to talk about some of the images that I've taken and some other potential applications of high-resolution TEM imaging of nanomaterials. And just to let you know, I have my contact information here on the first slide. You can also find that contact information on the last slide, and of course you can also find it on the website. So just a basic outline for this talk. I'm going to start by going through just a short introduction into TEM in general, use that to segue into an introduction into HRTEM and how that's a little bit different from regular TEM operation. Then I can talk about what we can image with the HRTEM, specifically crystalline structure of nanoparticles, nanotube morphology, and some atomic defects. I'll talk about some classes of atomic defects and instances where HRTEM has been used to image atomic defects. And then at the end, I'll include a couple applications of HRTEM in literature and some capabilities that we can have to do the same or similar things as well. So the basic operation of a TEM starts with an electron source located at the top of the TEM. The source generates an electron beam, and that electron beam passes through a series of electromagnetic lenses inside of the column of the TEM. And these lenses condense the electron beam and it condenses the electron beam right before it interacts with a thin specimen. And the beam's interaction with the sample is how we can get an image of the specimen, and that's one type of data that we can get. And we can also get other types of data, including diffraction, which I'll show, and EDS data as well. What we have here on the right is our Philips CM120. It's a 120 kilovolt accelerating voltage TEM. It's one of our 3 TEMs in-house at MVA. It's not our HRTEM. There's another one, an EM420, that I won't show in this presentation. It's another TEM that's not an HRTEM. And it looks very similar to the 200, but that's because most of the differences are going to be inside of the TEM and not outside. So what you see on the left here is just a morphology image of an asbestos fiber, and with morphology it's just a 2-dimensional projection of the specimen either onto a phosphor screen, which is located at the bottom of the instrument, or onto a digital camera, which we can then record onto a monitor and take an image such as what we have here. At the top right, we have a diffraction pattern, or selected area electron diffraction image, SAED. And with diffraction, the beam, once it interacts with the sample, it's scattered by the specimen, and an image is recorded, and this image shows a reflection that's indicative of the crystalline makeup of that area of the specimen. So you can see some vertical dots, some vertical columns of dots across this image, and I can index these dots, I can measure these dots, and can give some information about the crystalline makeup of that material, which in this case, this is indicative of an amphibole asbestos material, or just amphibole in general, but because of the EDS data that I'll be talking about next, I can put those together and say that we have amphibole asbestos. With the bottom right image, this is a plot, a spectrum for EDS, the chemical data that we can get with the TEM, and EDS is energy dispersive X-ray spectroscopy. With EDS, we condense the beam even more and that beam on a certain region of the specimen excites atoms. And once those atoms are excited, they emit an X-ray that's characteristic of an element. So if there's some silicon and we're condensing the beam on the silicon and shooting the beam at the silicon, it excites the silicon atoms. And once they're excited, an X-ray characteristic of silicon comes out. We have a detector that collects those X-rays, and then they're registered and placed onto the spectrum, and the software recognizes it as silicon, and then we have these profiles, and we can use that to come to some conclusions about the makeup of our material. So HRTEM is a little different from TEM. This is a TEM design with the capability to image at the atomic scale. We can use an HRTEM to directly image atomic lattice planes, along with some other nanostructures in materials that we normally would not be able to do with, say, our CM120. So this comes with some slightly different operating conditions. Normally, we're operating at a higher accelerating voltage, usually 180 kV or greater. And this is important because with a higher accelerating voltage, we're working with a denser electron beam, and when we have more electrons, we're able to produce more data, and in this case, it's usually a higher resolution. This possibly goes without saying, but higher magnification is required to image at the atomic scale. Without the higher mag, we couldn't image the atoms no matter what. And usually that's at 200 kx or greater, but that can vary quite a bit depending on how you have the camera placed, for example, in the TEM. And then there's some other high resolution components that help us achieve the highest point-to-point resolution possible. And in the case of our CM200, we have a high resolution pole piece, and this pole piece establishes boundary conditions for the magnetic field that controls those electromagnetic lenses I was talking about earlier. So a higher quality pole piece can better establish these boundary conditions, and this yields a better point-to-point resolution for our HRTEM. And as a result, we can get high quality spatial resolution, where the theoretically highest attainable resolution is at about 0.5 angstroms. Here we have an image of the Philips CM200. This is the TEM in-house that I use for HRTEM imaging. It's a 200 kV accelerating voltage TEM. As I mentioned earlier, it looks very similar to the 120, and the main difference is being that I can produce a larger electron beam, a higher voltage electron beam, and then also it has that high resolution pole piece that allows me to get the highest possible point-to-point resolution in the scope. And here's a comparison of a TiO2 nanopowder particle. These are two different particles actually, but they're from the same sample and located on the same grid, so I just took it out of the 200, placed it into the 100, and took an image of a similarly sized TiO2 particle, just to give you a bit of an idea as to how these images can vary in terms of the quality. The 120 is on the left and the 200 is on the right, and you can tell just by briefly looking at one versus the other that the 120, this is me pushing the 120 about as far as I would want to push it without the image getting really blurry and not great to look at, whereas what we have on the right is a much sharper image of the TiO2 nanopowder in the CM200. And you can even notice that running parallel to the crystal, we have some white and black lines running, and that's important for what we're going to be talking about next. So this is where we get into the crystalline structure of some of these nanomaterials. You can see that there are some black lines and white lines running parallel to the crystal, and this is just that same image previously on the right, but now it's up at 750,000 times magnification. You can see the scale bar of 2 nanometers in the bottom right. These lines that you see in this image are called lattice fringes, and these lattice fringes represent a periodic fringe in the TEM image, and this is formed by transmitted and diffractive waves that are exiting the lattice plane of the crystal. And these are best seen at a low Miller index face of the crystal, and basically what that means is that a certain face of the crystal that has a low Miller index has atoms that are stacked one on top of the other, and it makes it easier to see all the way through that column if they're all stacked perfectly one on top of the other perpendicular to the beam. What I've done here is just shown that the dark lines are the lines that represent where the atoms actually are, and the white lines represent where the beam is actually passing through the sample. So I have yellow lines over the black lines to show how I measured across these black lines to get a despacing, or the spacing between these columns of atoms in the crystal. So I measured across 8 and then just divided it by 8 to get a D-spacing for a single line from one black line to another. I could do it with one, but it's better, I get a more accurate measurement if I measure across multiple lines. And in this case, I got a D-spacing of 3.59 angstroms approximately. I believe it was like 3.586, for example. And compared to some other empirical data, XRD type data that I've obtained from TiO2 lattice spacing, this correlates pretty well with the 101 Miller index plane for TiO2. And what you see on the right at the top is a photograph of a large scale, what I would call a hand sample image of TiO2. And in the bottom right, it's a similar morphology TiO2 schematic that shows the 101 plane. So I'm imaging with the beam parallel, or perpendicular to that 101 plane. Having said that, there are some considerations that need to be taken into account when I'm attempting to image some lattice fringes and therefore lattice spacing for certain types of materials and types of sample preps. What I have here is a garnet powder, not a nano powder, just a garnet powder that I found a reference in the lab, and I wanted to drop it onto a TEM grid and see if I could get some crystalline structure from garnet. You can see on the left it's a larger, lower magnification image, and the yellow box is the inset that is on the right here, with the 20 nanometer scale bar. And just as a general description of this particle, you can see that there's some variability in the thickness, and that plays a large role in the point that I'll be making here. You can see in the center of the image some dots and some lines that the dots then make up. And running sort of vertical are these lines that I've highlighted in yellow in this area that I've highlighted in red, the entire like little circle there where you can see the dots. So I said, okay, we have something here to look at and to try and measure. So I measured the lattice spacing, or rather the lattice fringes, that's important, the lattice fringes of these spaces, and found that they were around 6 angstroms, which if I compare that to empirical data for garnet, that doesn't give me anything because there is no empirical measurement of anywhere near 6 angstroms for garnet. So it's an aspect of this particle thickness that needs to be taken into account, because particles that have a local variability in thickness can yield lattice artifacts. And this potentially leads to an analyst indexing a plane that does not exist. So it's important to know what you're looking at and that you have something that's relatively flat so that you're doing your best to avoid getting an image that has lattice fringes that don't represent actual lattice planes for that material. Ideally, you would have something like a thin film where everything is relatively flat and able to be imaged right down a very low Miller index plane. That's not always the case. So in these next couple images, I'm going to be showing some nanotube images. On the left, we have some single wall carbon nanotubes. And these, you can imagine them as just a kind of like the cardboard roll inside of a roll of paper towels, a single rolled tube, and in this case it's made of graphene. And they have some unique characteristics that separate them from multi-wall carbon nanotubes, in that they often exhibit superior electrical conductivity compared to the carbon nanotubes that are multi-walled, those counterparts. And there's images of those on the left. And on the right we have multi-walled carbon nanotubes. These are larger, these are more robust nanotubes. They don't have the same electrical conductivity that some of the single-walled nanotubes exhibit, but they are larger and more robust, so they serve some other purposes as well. So that's from a slightly lower magnification, and then we have a slightly larger one here on this slide. What we see on the left, it's actually a bundle of single-walled carbon nanotubes. If you look and see like the individual rolls that make up the bundle on the left, they're pretty easy to see on the far right of that image. You can see that there's maybe 8 to 10 individual carbon nanotubes that make up that entire bundle of carbon nanotubes. But the one that I find very fascinating is the image on the right of this is a singular multi-wall carbon nanotube. And in this case, you can imagine it more like the paper towels that wrap around the cardboard tube in the middle. And you can see each of those lines that make up the outside of that carbon nanotube, those walls, are more like each of those individual papers that roll around the paper towel roll. And I just find this an extremely fascinating image, that we can get an image of this quality. So we can characterize both single-wall and multi-wall carbon nanotubes and get some very high-quality, high-magnification images. So next I'm going to be talking about some atomic defects. So defects are just imperfections in the atomic structure within a crystal, within the crystalline lattice. And this can contribute to mechanical properties of a material. And in some cases, these are intentional and they're used to manipulate the properties of that crystal, of that material. So in the case of a cold working of a metal, that's deforming a metal at a relatively low temperature, lower than the recrystallization or the melting temperature of a metal. That increases the dislocation density, or the number of dislocations per unit volume for that metal. And that yields a higher hardness, a higher yield strength, a higher tensile strength for that metal. And that's obviously useful for certain metals if we're going to make tools, for example. So defects don't have to be bad things. Sometimes they can be used to manipulate them in positive ways. And I'll be talking about two different classes of defects. I'll talk first about some linear defects, mainly dislocations, and these are just irregular linear groups of atoms. And then I'll also talk about planar defects, which those could fall under grain boundaries, those could fall under twin boundaries, and I'm going to be talking about deformation twinning boundaries. So here we have an image of some linear defects, of some dislocations. And in this case, this study in 1993 was an HRTEM study of some silver-doped galena, where they were hoping to observe dislocations within the silver-doped galena. And you can see that there are some irregular-looking areas more towards the center of the particle in this image, and some of them are labeled E and some of them are labeled L. The ones that are labeled E are edge dislocations, and what edge dislocations are is just like an extra half plane of atoms that are within a crystal, and when you reach the end of that half plane, the crystal has to compensate for that, and as a result the crystal gets distorted, and that's why it looks kind of fat when you look at the E's that are in the center there. And then you have the ones labeled L, and those are dislocation loops. And you can see that they're much longer structures than the ones that are labeled E, generally speaking. The ones certainly in the middle are. And a dislocation loop is a three-dimensional interlocking network of dislocations. So with HRTEM, it's impossible to image the entire 3D network, at least through this method, image the entire 3D network of the dislocation loop, but you can at least see a partial section of that dislocation loop. And the entire goal here was to grow these galenas and characterize, and in a qualitative and in a quantitative sense, what was going on with these dislocations. How many were there? What was the amount in these galena crystals? Where were they? So in this case, they noted that a lot of them were in the center and not towards the fringes of the crystal, and just any other types of characteristics they could assign to the presence and the distribution of these dislocations. So that's a relatively easy thing to do if we can obtain a lattice fringes within a crystal. Next, we have some planar defects that can be present in some nanomaterials. In this case, I'm going to be talking about deformation twinning. You can see this on the schematic on the left. With deformation twinning, it's when a crystal lattice slips when it experiences some form of strain, and that yields twinning, or a point of symmetry in the lattice. So that red arrow in the schematic on the left represents the slip, and then it forms sort of a mirror. It's almost like it's folding, kind of like an accordion. So you can see that the lattice is running in one direction, it hits that red arrow, that boundary, and then it starts going in the other direction as if it's mirrored. In this study, the scientists theorized that nanocrystalline aluminum could exhibit deformation twinning, which is interesting because coarse aluminum, larger scale aluminum, has a very high stacking fault energy, and because of that it's very difficult to observe this type of twinning. So they took this nanocrystalline aluminum and ball milled it in liquid nitrogen, so basically just subjected it to some strain, took it out, placed it on a TEM grid and put it in the TEM, and lo and behold, in this image here you see to the right, they were able to observe a boundary for deformation twinning. As you can see in the bottom right image, you can see that the lattice above those arrows is running in one direction. It hits that boundary where the arrows are indicating that boundary, and then it starts to run in the opposite direction as if it's mirrored. So again, if we can produce some lattice fringes and see lattice inside of the crystal, it should be pretty easy to image the actual boundary for this deformation twinning, and for grain boundaries as well. So I'm also going to talk about a couple applications I'm going to start by talking about a semiconductor application. And in this study, they're dealing with these core shell nanostructures. And normally these core shell nanostructures are epitaxially grown, crystal to crystal epitaxial growth. And unfortunately, this type of growth requires a degree of compatibility between the core material and the outer shell material. So you can't mix and match as readily as you might like or might want to. So in this study, they grew core shell nanostructures via a non-epitaxial method, and they wanted to use HRTM to look at these combinations of core and shell to see if this growth method caused any sort of issues with the crystalline lattice, and they wanted to look at the lattice parameters of the core and the shell to make sure that there was no strain that was induced and that the actual lattice parameters reflected that of the actual material. And you can see in this image that you have some lattice fringes for various core shell combinations in this study, and in future images in this paper and index each individual lattice and show that this is consistent with this type of material. And then the final application that I'm going to talk about in the final content slide I'm going to talk about here is with some soot. In this instance, they're dealing with some soot collected off of a diesel particulate filter from engines running at two different types of load. Engine A, ENG-A on the left, was collected and run at 1500 RPM, a lower load condition, and collected onto a diesel filter and then analyzed via HRTM. On the right is engine B, and it was run at higher load conditions and then collected onto a filter and analyzed via HRTM. And the images from engine A, the initial images, those particles, those circular concentric particles appear more robust. They're more filled in, but not quite as well ordered as what you'll see in the as what you do see in the image B soot particulate. And then in engine B, these soot particulates feature an interior void. You can see that there's a space in the middle of those grape-like structures of soot. And also the outer shell appears to be a little bit more well-defined. The lamellae, the lines that make up the outer shell, are a little bit more defined than the ones in engine A, and they theorized that's because of oxidation and graphitization of these soot particles, and therefore there's a lattice that can actually be visualized via the HRTM. So because of their hypothesis that this engine B was just a more oxidized version of engine A because of those higher load conditions, they subjected engine A to oxidation after the fact and looked at it to see how it compared to engine B. And as you can see in the set of images on the right, these engine A post-partial oxidation particulate looks very, very similar to that from engine B. So it does look like that the oxidation played a very large role in transforming the particulate from what you see in engine A originally to what you see in engine B. And the take-home message here for soot is that chemistry is an important aspect of coming to a conclusion about what kind of material may have been burned to produce this soot, but we can also use some physical structures, and particularly via HRTM, to come to some conclusions about what may have happened to produce this soot. So to summarize, I started by talking about just basic TEM and some of our TEM capabilities with the CM120, our non-HRTM instrument. Use that to segue into HRTM and talk about the differences between the two and compared with that TiO2 particle. Talked about some crystalline features that we can observe in HRTM and how to actually measure lattice spacing, and some considerations that have to be taken into account when I'm looking at some particulate to ensure that I'm not measuring lattice fringes that aren't representative of an actual crystal lattice. I then spoke a little bit about the carbon nanotubes, the single and the multi-walled carbon nanotubes, and how we can directly image the structures, the actual walls that make up the multi-walled nanotube, for example. Then I talked about some atomic defects, the linear defects, those dislocations, the edge and loop dislocations in that galena, and planar defects such as the deformation twinning boundary that I showed for that nanocrystalline aluminum. And in these last two slides, I talked about some current or recent applications of HRTM, such as with those semiconductor core shell nanostructures and looking at the lattice for those two suites of materials. And then also the soot, and explaining how we can use HRTM to look at structures in the soot to come to some conclusions about potentially what were the conditions that produced that soot. And there are certainly many more applications. So that's it for me. I appreciate you guys taking the time to listen to my webinar here, and I will, I suppose, open it for questions now. And again, as I said, here's my contact information yet again.
Jake, thank you for your presentation. And now we're going to open the floor for questions. So you, all the attendees can type your questions on your box, and then we will address them accordingly.
I'll be making notes as you ask, so I'm making sure that I'm keeping all of this in mind.
One of the questions that we have is, did you investigate cast iron so far?
Cast iron, is that the question?
Yes.
I have not looked at cast iron yet. That sounds like something that would be super fascinating to look at, though.
Any other question so far?
And I'll chime in that I'm more than welcome to answer any questions after the fact if during this Q&A session you either can't think of one or come up with one, or would just for some reason rather ask it later. I'm more than welcome to answering those questions.
We have one that came up. The EDS can tell us exactly the type of elements, but what is the accuracy of the atomic ratio of these elements from the EDS data? Can we trust the EDS?
I always like to say that with the EDS, as far as atomic ratios are concerned, I always considered a semi-quantitative method. So, and in a lot of materials that I look at, there can be local changes in the chemistry anyway. So it's I think the long answer is that, or rather the short answer is that it depends on the material that you're looking at, how much you can trust the EDS, and that depends on, you know, both the user and the sample. It's probably not the very best approach to take if you really want to get a very detailed, thorough evaluation of what the chemical makeup is of a material that you're submitting.
Okay.
That's about it.
Have you done any work on carbon fiber or carbon nanotubes? I can address this one real quick. Yes, we have done a lot of different. We have image and acquired variety of materials, spanning from carbon fiber, carbon nanotubes, nano diamond, nano silver, all sorts of nanomaterials. We have image, and in fact, we are building a high resolution TEM imaging database where we are going to upload all of our high-res images on an online database. So once we have that, we will let people know to go browse around. Can transparent materials be characterized? Polystyrene to explore defect in molding such as strain?
I've never tried it, and so I don't know the answer to that question necessarily, but that's part of the reason for, as Ming mentioned, developing that database, is so that I can have that experience of looking at as many different materials as possible and having all that interesting experience attempting to look at and try and find some lattice and do other types of characterizations of these types of materials. So unfortunately, the answer for me is no, I have not looked at anything like polystyrene.
What I can add on to that is we have we have looked at a lot of different polymers with the TEM in-house for with a heavy metal staining to look at these different copolymer blends in the mixture. Okay, if there's any other question, then we will. If there's any more questions that come in, we will address them offline, and then we will send out a recording of the webinar to all the attendees. So if you would like to forward or rewatch this webinar, I can show you where to find them. Just a second. Okay, so here is our website, and then all of our webinars will be uploaded to our webinar page. So if you click into the webinar page, you will see all the webinars that we have done so far, and we will be uploading this recording to the high resolution TEM imaging page in the following week. So if you want to rewatch it, you can feel free to check it out or send it to your colleague. And this wraps up our webinar today. Thank you for attending. Thank you, Jake.
Yeah, thank you. And thank you, everyone.
Okay, goodbye.